Good morning, everyone. Thank you so much for joining me today for our talk on smart pointers, dumb mistakes. It's a lovely morning. The view is perfect from here, and I'm super excited to talk about this topic. Um, just a brief background. When I first started, like my first programming language was C. When I started, so I started with C, and eventually I moved to C++, and I also did Java for a bit. And I know that one of the most dreaded topics that anyone has to encounter when they start learning C++ is pointers, because it's really hard to understand what's happening, what memory is it referring to. So we all know that a pointer is a reference to some memory, right? So memory management becomes an issue in large scale systems. There are so many scenarios where memory leaks are happening and system alarms are going off. So it's really interesting to see how memory management works in C++. And as C++ is advancing more, there are better ways to do memory management, and smart pointers were introduced just for that. So before I begin, I would like to give a quick introduction about myself. So I'm Khushboo Verma, and I'm traveling here from India. This is my first time at CPP on C, and the energy here is enthralling. I'm really loving the vibes. So I currently work at a company called Appright. I'm a platform engineer there. Appright is an open source backend as a service, and we offer functions, serverless, function sites, storage, authentication, everything under one roof. So before we start, let's do like a quick exercise. So you would see like a quick snippet on the screen, and I just want you to spot the bug. Like, just tell me, like, what's going on? What's wrong here? Anyone who would like to, share? I think we have someone there. Can we pass the mic?
Thank you. Um, there are two pointers to two loading pointers to the same memory block or case memory block.
Yeah, that's correct. So if you all have been working with C++ for some time, you all know that the power pointers give to us, but at the same time, they also, bring a lot of pain, and managing them is difficult, and we all make obvious mistakes in code now and then. For decades, managing memory in C++ involved a lot of manual new and delete operations, right? Which, let's to be honest, it was like little hard. Sometimes we used to forget to call delete in different flows where the flow was going if the errors were coming. And situations like these happen, where we might address some memory and we do not realize like what's exactly happening behind the scenes. So you know uh, let's say that this is like a bug that it's very frequent to see. So we can see in the first line that we are using a unique pointer, and we are using make unique to point it to a particular address. And then in the second position, I'm again doing, so I'm referencing that pointer, which is ARR, and I'm doing ARR.get, and I'm, addressing it. So initially, if you look at the first one, it is like a pointer to a 10 array of size 10. So if I do array get plus 5, it is pointing to the sixth position in the array, right? So unique pointers, as we'll see further as well in the slides, that they automatically get deleted. So in this particular case, it will try to delete it twice when the memory goes out of scope. So this is exactly the problem that's happening here. A double deletion is happening. So as I said earlier, like the array was actually pointing the array was like an array of size 10, and it would have called the delete array operation, right? And when I do a get operation, it is pointing to the sixth position, and when that line ends, it is going to try to delete that location again. So as a rule of thumb, always try to have clear ownership. Like, okay, what if a memory is there, like who is exactly owning it, who is responsible to manage it, and who is responsible to clean it. So there needs to be clear ownership there. So now, let's just take a step back and let's talk about, why are we even discussing this topic? Why this talk is even important? So, we all know that there are so many big companies and there are so many bugs that happen in production. So these are some statistics that I was looking at recently, that Google has reported that 70% of their security bugs happen because of memory issues, right? And I have personally seen a lot of memory issues in production, and I'm sure that all of us have. And even Windows has been having a lot of these issues. I used to work at Microsoft before, and I have seen, how these challenges used to creep in every now and then. And we know that smart pointers are introduced, but smart does not just mean magical, right? There has to be certain gotchas to it, like certain things that we need to take care of as developers. Just because it is smart does not mean it is going to take care of everything automatically. And so, what we will cover in this particular slide, first of all, we'll talk about raw pointers and why they're still relevant today. And then we'll talk about different types of smart pointers like unique pointer, shared pointer, weak pointer. And we'll also talk about the tools that we can use to catch these issues early on. So these statistics just show the importance of why it's so important, and we'll see some examples of commonly introduced bugs that we can all make time to time. So yeah, before starting, let's talk a bit about raw pointers, which are the foundational topic, right? So why we start here? Because smart pointers are actually built on the concept of raw pointers. Underneath, it is still doing the same thing. It is still using the new and delete keywords, right? So it's really important to understand the ownership and the semantics of what's exactly happening. And exception safety is nearly impossible to get right manually. Like, I have made a lot of mistakes, and again, we keep seeing those bugs where some memory leak is happening or something is going wrong in very few scenarios, and it's really hard to debug it. And smart pointers actually help us automate RAII for us, which we'll talk in just a second. But if we look at the code snippet in the slide, so it is using the new keyword to allocate memory. And whenever we use the new keyword, it's very important to also delete and deallocate the memory that is being used. So if you look at the snippet, let's say that there is an error condition, right, which is unexpectedly terminating the entire flow. So in that particular case, as we can see here, that the return statement is returning it, and somehow the developer forgot to call the delete operation there, so it would lead to a memory leak, right? So as we can see that in the normal flow we had added the delete operation, but there are certain scenarios where an error might occur, an exception might occur at a certain line in the code, and it might not deallocate the memory. And in small scale, it might not be relevant, but if you're running huge production systems, then these small leaks become huge, right? And they can bring an entire server down. So it's really important to start there. Now, we all know about RAII principle. It is the resource acquisition is initialization, right? So what it helps in ensuring is that first of all, automatic cleanup happens. So whenever anything goes out of scope, there needs to be an automatic cleanup that happens so that we do not make those mistakes. And there needs to be exception safety. Whenever an exception is occurring, we need to ensure that we exit through the program in a safe manner. We just do not terminate the program in an unexpected manner, and no memory or resource leaks should happen. So some common RAI classes that we all have been using in C++ are unique pointer and shared pointer, which we are going to talk about. So these are the smart pointers. And then we also have vector and string in C++, and that's the reason we do not do new vector. It's automatically taken care of in terms of managing this dynamic memory. And then we also have IOStream and all of these file handling things, all the file handling classes, they're also following RAII. And then the mutex logs, the log guard and the scope logs, they're also using this. So we all know that any resource which either it could be memory or it could be sockets or files or logs, these need to have a constructor and a destructor. And what happens is that in RAI, it ensures that the resource, it ties the resource management to the object's lifetime. So once the object goes out of scope, it automatically does the memory cleanup for us. So the destructor is automatically called when the object goes out of scope. And exception safety is there by default. But implementing all of this correctly could be error prone. And this is where, smart pointers shine in. They implement RAII for us. So we do not make the mistakes that, were there in raw pointers previously. So let's first talk about what is unique pointer. So unique pointer, as the name suggests, it is pointing to a unique location in the memory, and it means that it has exclusive ownership over the resource that it is accessing, which means that unique pointer cannot be assigned to two memory locations at the same time. It can only be moved, right? So if we look at the code on the screen, it says that auto pointer is, we use the make unique function, and you always use this and we pass the resource that we're trying to make unique. And what it promises us that there is going to be automatic cleanup. So whenever the scope goes out, the memory is going to be clean. So you do not need to call delete manually. And then it is exception safe. It has the move semantics, as we mentioned. It is going to move the pointer. So if it was pointing to one location in the memory and then you want to access another location, it's now going to move from here to here. It's not going to point to both the locations at the same time. And it has zero overhead. And we'll talk about performance just in a bit. But if we look at the basic usage syntax there, so you can initialize unique pointer. I would like to point out that it is a part of the memory header. So if you want to use unique pointer, you can do hash include memory, and it's going to be included. And so you can initialize it. It has like the template. So any type of data, it could be an integer, it could be a string, or any other data type. You could initialize it. And if you use the make unique, it is gonna initialize it properly. And you can also use it for arrays, as you can see on the screen here. So, and if you want to move it now, then there is the move function that you can just call. So essentially, just to summarize, it is representing exclusive ownership. It cannot be copied, it can only be moved, and it has zero overhead. But there is a catch there that if your builds are optimized, then unique pointer does not have much of an overhead. It is pretty similar in performance to raw pointers, and it is exception safe. You can prefer it over new always. And the array version automatically uses delete array instead of just delete. So it automatically takes care of all of that for us. Now, to talk about some gotchas, some things that, can happen, some common mistakes that we can make. The first one, as I mentioned, is double delete. So in the previous example as well that we saw that, whenever we use get, it is actually returning the raw pointer, but it does not transfer the ownership. So if you do something like this, like if you do a make unique and then you try to do ptr.get, that's just going to return a reference to the raw pointer. And if you try to do that, the destructor will try to trigger again, and it will try to delete a memory location which has already been deallocated. So double deletions are very common. So just a rule of thumb there is to keep in mind that do not try to use get and then delete at the same time. So this is one of the most common unique pointers bugs, I think, that is that happens. And you know s- even in the second example, like we can see that when we are doing in star raw, and we're doing pointer.get, and then I'm again trying to use that pointer inside my unique pointer. In both of these cases, there are going to be unexpected behaviors that we will see, and both will try to delete the resource when they go out of scope. So only use get when you're trying to pass raw pointers to functions. Do not try to use them in conjunction with unique pointers. If you're doing, please try to understand that. Please try to ensure it is not trying to delete memory multiple times. It is only deleting it once. So this could be one of the scenarios which could be problematic. The other one is where we might confuse between arrays and single objects. So again, just to look at the code in the first one, so there is this undefined behavior happening where I'm initializing the unique pointer and I'm pointing it to an array. So I'm again initializing it to an array of size 10, and whenever it's going to go out of scope, it would. So notice here that I'm creating a unique pointer of type integer, but then inside the array, I'm doing new int. So I'm using new keyword and unique pointer in the same exact line. And what it's going to do is that because it is a unique pointer of type integer, when it goes out of scope, it would call delete and not delete array, right? So in that case, it would be having unexpected behavior. So what would be a better way to write the same code? What we can do is that we can actually initialize it. If I'm doing an array inside it, then I need to pass array here as well. So in the unique pointer, I need to do int and then array. And otherwise, I can obviously use make unique, and that's going to take care of it for me. So this is a subtle but critical distinction. And using delete on memory allocated with new array is undefined behavior. So the compiler might not catch this mistake. And it's always a good idea to use the array versions for arrays and single objects versions for single objects. So try not to mix both of them. So unique pointer integer will expect a single object like new int and not new int array. So that was another gotcha. Now the third one that can usually happen is when custom deleters go wrong, right? So let's say that in the code example here, so there is like a cleanup counter, that's an integer that I'm maintaining, and then I have a lambda function which is deleter, And as you can see that it has like a pointer, and here I'm trying to capture it by reference. And if you see, after below this lambda function, I'm creating a unique pointer where I'm using this deleter, right? So custom deleters are very powerful, as we all know, but they can also be dangerous if not, managed well. So if we try to capture local variables by reference, it could be a common mistake. So the deleter might be called after the captured variables are destroyed, right? So it could happen that it goes out of scope, and after that we are trying to delete that particular memory location. So in this particular case, the pointer can outlive the function, and after that it would try to delete some dead memory which does not really exist there. So in this particular case, we are capturing the cleanup count by reference inside the lambda function, as you can see. And then I'm trying to use this lambda as a custom deleter inside my unique pointer. So in this case, the cleanup count is a stack variable, right? And it would be destroyed whenever the dangerous deleter function is going to return. But the lambda inside the unique pointer will still hold a dangling reference to this particular memory location. And when this PTR would be destroyed later on, it will try to access the cleanup count variable, which is a dangling reference. It does not exist now, right? It would cause an undefined behavior. So why is it dangerous, right? It is dangerous because the unique pointer is storing the deleter by value. It is not storing it by reference. And this means that the lambda is actually copied inside the unique pointer, and the lambda is capturing a reference to a local variable, and the reference becomes invalid when the function returns. And any access to any cleanup count variable after that, it's going to result into a use after free error, which means that you're trying to use a variable after the memory has been freed. So try to avoid these scenarios where you're trying to access something which might go out of scope, even before you try to access it. So that was about unique pointers. Another popular smart pointer we have is shared pointers. And as the name again suggests, it has shared ownership, right? So if we look at the syntax, it promises that, if I create a pointer which is pointing to one memory location, this pointer can also point to another memory location. So it's like a shared pointer between both of these memory locations. So just like we had the make unique, here we have make shared. And I can pass the resource inside it. Now this resource could be any data type. It could be integers, it could be string, it could be arrays. And as we can see, in the second line, I'm doing auto ptr2 equals to ptr1. So what shared pointer actually does is that it maintains a reference count underneath. So it tells me like how many memory locations am I trying to access with this shared pointer. And object is destroyed when all the shared pointer resources are destroyed. So when the last one gets destroyed, that is when the shared pointer is also destroyed. So if I talk about a couple of key concepts here, it is going to track how many shared pointers are pointing to a single object, right? And it is going to store these reference counts and other metadata inside it, which is why it has a bit more overhead as compared to raw pointers, because it is keeping a count of how many objects, of how many pointers are referencing to a particular object. And it is this reference counting, it uses atomic operations. I would like to point out that reference counting is thread safe. So if multiple threads are initializing pointers to the same memory location, in that case, it's going to be a thread safe operation. It's going to work perfectly fine. And objects are destroyed when the count reaches zero. So if there are multiple pointers pointing to the same location, it would be destroyed when the reference count becomes zero, right? So it enables shared ownership. It has multiple pointers to the same object, and the reference counting is automatic. And it has more overhead over unique pointer as well, because it has control block and the atomic operations, but it solves problems that unique pointers can't handle. That is why it is important to use shared pointers in multiple scenarios. But there are, let's talk about the control block that happens with shared pointers. So if we look at the example here, so I'm making two allocations here. If we look at the first line, so I'm initializing a shared pointer of type integer, and it is called ptr1. And inside it, I'm doing new int 42. So as you can see in the same line, I'm also doing shared pointer, and I'm also using the new keyword. So it is an object allocation and also a control block allocation. And if you look at the second line, I'm doing auto ptr2 and I'm doing make shared and I'm creating an integer, right? So in this particular case, it's just a single allocation. So the control block is having the reference count. It will also have a weak reference count, and it will have custom deleters and allocators. So basically, each shared pointer has some metadata that it is storing there. So it has some memory overhead as compared to unique pointers, and it is going to maintain all of this internally for us. So this is a crucial performance consideration. So, the weak reference count for weak pointer support, we're going to see in a bit. So there are also a couple of gotchas with shared pointers. So when you're using shared pointers in production, there are a few things to keep in mind. The first one is a circular reference. There could be a circular reference death trap where a parent class is, referring to the child pointer and the child is pointing to the parent. So in the below example, you can see that we have a parent class. Inside in the parent structure, I have like a shared pointer and it is pointing to the child. And then I have a child structure and it has a shared pointer and it is pointing to the parent. So as we can see, there's a cycle. And since both of these objects have interdependency on each other, it's never going to go out of scope and it's never going to get cleaned up, right? So if you look at my code below, I'm initializing both of these structures. I'm making them shared, and I am trying to, make that the parent has reference to child and child has reference to parent, and it is going to result in a memory leak, right? So the key insight here is the reference counting cannot handle cycles. So this is a fundamental limitation of reference counting's garbage collector. Languages like Python have cycle detectors, but C++ does not. So we need to break the cycle manually somehow, right? So how can we do that, right? In this case, we can actually use something called as a weak pointer. So the weak pointer, or I can also call it the cycle breaker in this particular case. So I will like to show you how I'm using this in the below code example. So similarly, just like previous example, I'm creating a parent structure and I'm creating a shared pointer to the child structure. But inside the child, I'm not creating a shared pointer now, I'm creating a weak pointer. So the weak pointer is now pointing to the parent, and this is now a correct implementation. And it is a safe usage because as you can see that now uh, the parent is alive, and I can just track like when is the parent alive. So weak pointer is basically holding a weak reference which does not affect the reference count. Okay, so whenever we are using weak pointers, please note that you need to use locks there for safe access. So try to use lock whenever you are using weak pointers, and the lock will return an empty shared pointer if object was already destroyed. So if I want to check if an object actually exists, I can check if the lock is returning an empty pointer to me. And if I do that, I know that when the cycle is breaking and I can, just end the logic there. So only the parent in this particular case is holding a strong reference to the child structure. The child structure is holding a weak reference to the parent. And when the parent is destroyed, the child will also be destroyed basically. So there are certain usage patterns where I think weak pointers suit very well. So in this particular case, in the observer pattern, so the observer pattern is a perfect use case to, for weak pointers. So the observers, let's say that there is a subject and there are multiple observers there, right? So observers should be destroyed without notifying the subject or having any dependency on the subject's lifetime, right? So the subject should automatically clean up all the dead observers, right? It should not happen that, they have interdependency and one is, there's like a deadlock situation where one is trying to, depend on the other's life cycle. So in this particular case, there would be no memory leaks, there will not be any dangling pointers, and this pattern is actually extensively used in all the GUI frameworks. So if I talk about the code very quickly, so I have a subject class, and inside it, I have a vector of a weak pointer. So basically, I'm maintaining a vector of all the observers that I have. And then I'm using a notify function, and I'm iterating over all the observers that I have, and I'm trying to first check if the lock is returning something, right? Only if the lock is valid, in that case, I'm updating my observers and I'm incrementing the counter. Otherwise, I know that the subject is probably not there anymore, and I can clean up all my dead observers. So this is a safe thing. No cycles would happen here. So try to use weak pointers in conjunction with shared pointers to make sure that the memory is cleaned up properly. But let's also look at how the lifetime or life cycle of a weak pointer works. So Inside the scope, the weak pointer can be locked to access the value, and outside the scope, the shared pointer is destroyed. So weak pointer becomes expired. So let's talk about the code line by line. So I'm initializing the weak pointer life cycle. Inside it, I'm initializing a weak pointer, and inside that, I'm initializing a shared pointer. So I'm then pointing the weak pointer to the shared pointer. So the weak pointer is observing my shared pointer's location. And then I'm checking if the lock is still there. So if I'm checking if the weak.lock is there, that means that my weak pointer is still alive. So I'm going to enter that condition, and let's say I'm just doing some logic. In this case, I'm just printing that that I'm inside the scope and the pointer is alive. Otherwise, if the lock returns an empty reference, it means that the the shared pointer is no longer alive, and I can see that the weak pointer has expired, right? And after that, the shared pointer is going out of scope, and I can also check if the weak pointer has expired outside the scope as well, and it will tell me if it is expired or it is still alive. So basically, it is preventing these dangling references by not extending the object's life cycle or lifetime. Now, there are more gotchas to using shared pointers. Another thing that could happen is aliasing the constructor trap. So, the aliasing constructor is a little known but dangerous, right? So, it creates a shared pointer that points to a different object than it owns. And it is useful for pointing to memories of larger objects. So, if we talk about the code, I have a big data structure here, and inside it, I have a vector which, let's say, is a huge vector. It could be 1 MB in size or 10 MBs in size. And then I have a small integer in small value. And then I have a big data, and you're making this a shared pointer. Now, if I try to make a shared pointer with the small pointer where I'm referencing this big data, so let's say that I just wanted to access a small integer or a small value, right, in this big data, and I'm using, this pointer for that. In this case, the big data won't actually be destroyed because the small reference is still pointing to that big data. So basically, it is creating a shared pointer, and it is useful for pointing to the larger object. But what is happening is that it is keeping the entire object alive, even if you only need a small part. So let's say that there was a really big file of multiple MBs, and you just still needed a reference to a small portion. That's not good practice because it is still going to keep the entire object alive in the memory, and it can cause significant memory bloat in the long running application. So after that, another one that could happen is the thread safety misconceptions that people usually have with pointers. So a very common misconception that people have with smart shared pointers is that many people think that shared pointers are truly thread safe. That's not the case. So the atomic reference counting is protecting against double delete. So the reference count inside a shared pointer is thread safe, but shared pointer itself is not always thread safe. So copying or assigning shared pointer needs synchronization, and the object being pointed to needs its own thread safety. So whenever you're using shared pointers, please ensure that you take care of thread safety. You ensure that multiple threads might not cause problem. And whenever you're using shared pointers, always try to use mutexes and locks to ensure that shared pointers have proper sharing between different objects. So just to give an example of what could go wrong in a production system is that if I'm creating a shared pointer, which let's say in my case is called global pointer, the first thread is actually, global pointer is thread one. It is referring to the shared pointer by using the make shared, and it is referring to a position. But then I also try to create another thread by using the get, auto local is global pointer. So in this case, it's going to have a race condition, right? So the shared pointer itself is not thread safe, and only the reference counting is thread safe. So please make sure that you're handling it properly with locks and mutexes wherever applicable. Now, again, another gotcha that in shared pointers that could happen is that exception safety is a common thing. So this is a subtle but critical exception safety issue that could happen. So in this case, if I show you, what I'm doing is I'm creating a process where I'm initializing a shared pointer and I'm doing new A inside it, right? And again, I'm doing shared pointer new B. So, there it could happen in any order. So, but what it will try to do is it will try to do new A, new B, and then it will try to create a shared pointer using that. But let's say that if the new A happens and the new B fails, the new A is still gonna be dangling somewhere. There is not gonna be a proper cleanup that would happen for that new A that was already done. So in case any exception occurs in this particular line, then I'm gonna have again dangling pointers and memory leaks. So this is not a good way to write this particular line. So just below, I have shown a safer way of writing the same thing. So if I can just actually create a shared pointer for A, and then I can do for B. Basically, inside behind the scenes, it is again calling the new pointer. But if I'm calling the first line, it ensures that the A was completely like created properly, and there were no exceptions or no dangling memory. The memory is gonna be cleaned if any exception occurs in the first line, and the second line won't be executed. And then once I have initialized both of these using make shared, then I should call them, pass them inside the process function that I have. So basically, there's no particular order in which it might happen, but if one of these fails, it's gonna cause memory leaks. And the make shared will actually prevent this by ensuring that no raw pointers are existing, and make shared and make unique are strongly preferred. So whenever you're doing like a shared pointer initialization, please try to use it along with make shared. Just like unique pointers have make unique, in case of shared pointers, always try to use make share, right? So that's there. And now let's do like a quick overhead comparison between different pointers. So in this particular presentation, we have talked about raw pointers and then unique pointers and shared pointers. If I talk about a typical 64-bit system, in that case, if I talk about in terms of size, a raw pointer is gonna take 8 bytes of memory. A unique pointer is also gonna take 8 bytes of memory. A shared pointer might take 16 bytes of memory. The reason is that, raw pointers do not have any overhead. In the previous example, I also mentioned that unique pointers also will not have any overhead if the build is optimized. If the build is not optimized, there might be some overhead in comparison to raw pointers. But in case of shared pointers, we have the control block, and we are also keeping a lot of metadata. In terms of metadata, we have the reference count, we have the weak reference count, and we also have, the deleter and allocator and stuff like that. So it is going to have some overhead. So it also has these atomic operations that it performs. It is keeping the incrementation of the reference check. It is checking if it is 0 or not. So a lot is going on there. So in terms of performance, in shared pointers, the atomic increment and decrement are happening on copy and destroy. So these numbers are actually typical. They are not exactly, they might vary based on different systems, but these are just like a reference of a general system. And the unique pointer, like just try to optimize it. In that case, you will not have any major performance issues as compared to raw pointers. And the atomic operations that happen in the shared pointers can be expensive if they are happening in highly contended scenarios where there are like multiple shared pointers pointing to the same object. So it might get messy there. But again, like as I said, that smart pointers are not a perfect solution to every scenario. So if you have a use case where you do not need a shared pointer, where there is no shared ownership of a resource, I think you might be better to use, unique pointers or raw pointers. So it's not the best solution to every problem, but it is good enough in situations, where your use case is actually suitable. So there are actually certain tools that you can use to detect and prevent these scenarios from happening. I know that a lot of modern compilers also issue these warnings when you try to access the unique pointers or the memory in an unsafe way. Like for example, when I run a couple of code examples, it tells me that there is a use after free error, which means that I'm trying to use a memory after I've already freed it. But not all compilers might point out these issues. So what I can suggest is that you can use static analysis tools whenever you are, writing production code, and you can just run these static analysis to see like if your code is violating one of these, things, and if there are any memory leaks or any resources that might not be properly deallocated. So the CLang static analyzer is actually built into the CLang. It catches many smart pointer issues when you try to run it. Then there is also a paid solution, which is the PVS Studio. It's a commercial product, and it has this smart pointer specific checks that will point out if your smart pointers are not used in an appropriate way. And then if you want to use something free and open source, then there is CPP check, which is open source library which has basic smart pointer validation. It can do some basic validations for you. And these tools are essential. So if you're running any production system, I would highly encourage you to implement them in your CI/CD pipelines to make sure that we catch issues early on before they happen in production systems. And if you want to do it in the runtime, then there are also certain options on the right side of the screen. The first one is the address sanitizer. I think it is best for use after free or double deletion errors. So it is gonna point out at runtime, and you can look at the logs, and it is gonna tell you. So there is this command that you can actually run at runtime to check it. It is g++ fsanitize address, and you can run it with your program. So it is incredibly fast. It is going to catch most of the issues that might happen in terms of smart pointers. The other option, which is very comprehensive but it could be a bit slower, is this val grind. So you can actually run it as well, and it is going to go through your entire code. It's going to point out any potential issues that might be happening. And then there is also thread sanitizer that you can actually use to check race condition between threads. And whenever you have highly concurrent systems, in that case, it might be better to check if multiple threads are trying to access the same memory location in an unsafe way. So for that, you can run this fsanitize thread, and this is going to tell you like if there are any certain things happening in the system. And static analysis will catch things at compile time, and these are the runtime tools that you can use at runtime. And I would say that there is no excuse not to use these tools in modern application development, because if we can catch issues early on and they can prevent huge downtimes, then I think it's really good to check. But this is like for these are tools for detection. But I think as developers, the best thing is whenever we are writing any code which is involving the pointers, we just need to ensure that no flows are broken there, and we just ensure that memory is properly allocated and deallocated. And also, it's very important to check for every scenario that could happen, right? If there could be multiple exceptions, just need to make sure that every single flow is taken care of. There shouldn't be no situations where memory leaks could be happening, because even I have worked in production systems where it happens that only 1% of the users are facing an error of there's a error which is really hard to reproduce. It happens only in certain scenarios. So it's really good to make sure to keep these practices in mind. But so if I have to summarize the best practices as developers that I also keep in mind, and you all can also keep in mind, is that always prefer to use make unique or make shared over the new keyword or the delete keyword, because these are implemented to make sure that the common mistakes do not happen. And as a developer, you do not need to manually handle all the things that happen behind the scene. And whenever you are using shared pointers, try to use weak pointers to break cycles, to ensure that no deadlocks happen, no cyclic dependencies happen. And whenever you're using get, only try to use it when you're using with C APIs, because as we saw in a couple of examples, that if you're trying to use get with unique pointers or shared pointers, double deletion or more error scenarios can happen. So avoid to use get wherever possible, and be very explicit about custom deleters. You need to know like when it is being used, what exactly is it doing, and a proper cleanup needs to happen. And in your CI/CD pipelines, add sanitizers. Make sure that there are static code analyzers and runtime analyzers which are capturing these errors, and you can catch them early on. And you should also have some profilers, which are optimizing and the reference counting is happening properly. So this, and also try to understand the ownership of the semantics clearly. Please understand like you need to know like this is my pointer, which memory location is it pointing to, and what exactly needs to be the ownership of this pointer. If you feel that this is a location which this pointer is not supposed to access, or this might not be even relevant right now, make sure to clean up all of that code. And it also becomes relevant when we are doing code reviews. So if you are someone who is doing code reviews, then make sure that the raw new and delete pointers are not mixed with shared and unique pointers. There needs to be like a clear distinction. If we try to use everything in the same line, it might lead to unexpected behaviors. And whenever you see that the get is followed by delete, please make sure that it double deletion or something like that might not be happening. And whenever there are single owner use cases where there needs to be a single owner of a resource, and someone has used a shared pointer, please try to see if it was actually relevant there. And if there are parent-child relationships, make sure that it is a weak pointer is also used in conjunction with the parent shared pointer so that the cyclic dependencies do not happen. So these rules will most likely prevent 90% of the issues that you might face with smart pointers. And every team, every engineering team should make it a part of their general, coding standards or code review practices. And code reviews, if your company has any code guidelines, please make sure to mention that developers need to look for these particular patterns in their codes. And obviously, as I mentioned, that a lot of automatic tools are available there which are going to detect these issues for you. But it would be great if these do not happen in the first place. And the goal here is to make the code safe by default and not in exception scenarios where an error occurs and then we go and debug why it happened in the first place. So if we just keep good coding standards and practices in mind, it will help us avoid a lot of production scenarios. But there are a lot of cases where people will say that hey, we already have legacy code, and there are already new and delete pointers, and it happens. There are multiple organizations which have huge code bases since couple of years, and there are places in your code where these might already be there. And if you are someone who is trying to migrate from that previous standards to using smart pointers in your code, I have a couple of strategies that you can use to migrate your legacy code. So the first one is, I would recommend starting with leaf functions, functions that don't call other functions, which are simpler functions. Try to start there. you know and then you can also use static analysis in your existing tool. So make small changes, make sure you run the static analysis to make sure that no new bugs are introduced. I mean, we all know that the horrors of touching legacy code. Sorry. So touch legacy code carefully, do not break it. And whenever you're making small changes, try to start with flows which are not very closely coupled. Try to find leaf functions which are not having dependencies on other functions, and migrate one module at a time. Try to ensure that it is working as expected. Try to run the static code analysis and also the runtime analysis to see that no new bugs or unexpected behaviors are introduced. And if possible, try to add tests, unit tests, end-to-end tests for all possible scenarios, so that these whatever code changes you make, they do not cause any unexpected new behaviors in the systems. And use tools to verify that there are no code regressions happening. And some common patterns. So for example, if before you had a function like void process data, where you had a data pointer and it used to work with raw pointer, what you can do is you can actually replace this data pointer with this shared pointer, right? And you can just pass it. It would work the same way, but the ownership would be clearer. There would be like a clear distinction of who is owning a particular resource, and there probably will not be any mix-ups. So I know like legacy codes are really hard to change, but if we want to make systems better and avoid wasting half of our time in just solving bugs that happen repeatedly, I think it's better to slowly transition into newer standards and just make code better. So that's it from my side today. Thank you so much for all your time, and now I would be open to take some questions.